All right, let's cover Unit 8 for our study guide, which is acids and bases. Before we start, we have to establish some equations that are given to you on the test, and one of them is actually not given on the test, so you should probably know. So starting off with the ones that are given, you're given pH equals the negative log of the concentration of H plus, pOH equals the negative log of the concentration of OH minus, and you're also given concentration of H plus equals 10 to the negative pH, and the concentration of OH minus is 10 to the negative pOH. All right, and the one equation that you are not given is pH plus pOH is going to be equal to 14. This is important when you're calculating pOH or pH when you're given the one part of it. So if you're given pH and they ask you to find pOH, you need this equation. Vice versa, if you're given the pOH, you need to find the pH, you need this equation. So this is an important equation that you must know that is not given on test. This is not given on test. All right. And this number right here is 14 just because the pH scale goes from 0 to 14. And just got started on the table. So you're given pH and you want to find the pOH. This is very simple. All we do is use this equation. Same for this one. We have the pOH and we need to find the pH. We take the pH and subtract this from 14. Then we get the pOH. Doing that, we take 14 minus 2.37, and that gives you 11.63. 14 minus 8.41 gives you 5.59. Write that 5 a little neater, 5.59. And for the pOH, same thing, we minus 6.92 from 14, which gives you 7.08 for your pH. Based on your pH, we can calculate whether a substance is an acid or base, which we are going to do. So pH of 2.37 is less than 7. It is an acid. pH of 8.41 is greater than 7, so it is going to be a base. And 7.08 is going to be larger than 7, just by a little bit, which makes it a base, so a very slight base. All right. Now, figuring out the concentration of H plus is very simple. All we got to use is this equation. So if you're given pH and you're solving for H plus, we can use this equation here. Same for solving for the concentration of OH when you're given the pOH as well. All right. So what you do is take 2.37 and you're gonna get your calculator and you're gonna do 10 to the negative 2.37. So it'll look like 10 to the, or sorry, I'll put it on this box. 10 to the negative 2.37, which is going to be basically what you're going to do to find the concentration of H plus, and that is all you do. So with this information, we plug it into our calculator, and you get 4.3 times 10 to the negative 3 molars. So concentration, we have to remember, is always in molars. So I'm actually going to go ahead and put labels on all of these boxes for the concentration of H and OH because it is missing them. And we know that there is no label for pH and pOH. It is just a number. For my calculator, I am going to be rounding to whatever looks the cleanest. Usually you round to the nearest sig figs, but the test is multiple choice. There's no need to do that. You'll recognize the answer when you see it immediately. All right, so going on, using this H plus, we're gonna figure this out using the same equation we did. 10 to the negative 8.41 is going to be equal to 3.89 times 10 to the negative ninth. All right. So next up, we have let's finish these two right here. Kind of going out of order, but we're going to go ahead and try to solve similar problems first. So since we have the pOH calculated, all we got to do is plug it into this equation this time, since we're solving for the concentration of OH. And all we do is 10 to the negative 11.63, which is going to give you 2.34 times 10 to the negative 12th. Negative 12th. Same for this, 10 to the negative 5.59 will give you 2.57 times 10 to the negative 6th. All right, this time we look here, and the only data given is this, the concentration of the OH. When we have this, we can also calculate the pOH with our equation. All we got to do is negative log of this. So negative log of 6.99 times 10 to the negative 9 is around 8.2. I'm going to round, as I've said before. So based on this information, we can go ahead and calculate the pH. All we do is minus 8.2 from 14. And we get 5.8 for our pH. Based on this, we can go ahead and calculate our H plus. We do a 10 to the negative 5.8, which is going to be 1.58 times 10 to the negative 6. All right, next up, we're given the concentration of H plus, and we're asked to find the pH. Based on this and our previous accounts with our equations, we can, let me just erase that real quick, actually, on top. Okay, that's not good. All right, yeah, we'll just leave the circle, whatever, it's fine. So based on this, we can find the pH. All we got to do is use this equation, the negative log. So negative log of 8.74 times 10 to the negative 12 is around 11.05. Subtract 11.05 from 14, you're going to get 2.95 for your pOH. Based on this pOH, we can go ahead and excuse me. We can go ahead and calculate the concentration of OH. So we take 2.95 and we plug it into this right here. 10 to the negative 2.95 is going to be 1.12 times 10 to the negative 3 molars. All right, next one, we were given both the pH and we're given the pOH and we found pH. So to find the concentration of OH and concentration of H, all we do is for pOH, we're going to go ahead and 10 to the negative 6.92, which gives you 1.2 times 10 to the negative 7th molar. Same thing for concentration of H plus. We're going to get our pH. Do a 10 to the negative 7.08, which is going to give you 8.32. 8.32 times 10 to the negative 8th. Last one, or second to last one, we're given 1.3 times 10 to the negative 5 as our concentration of H plus. To find the pH from this, we do a negative log of 1.3 times 10 to the negative 5, which is going to give you 5. Based on this, we calculate our pOH. 14 minus 5 is going to be 9. And we can type this into our equation for OH. 10 to the negative 9th. So it's going to be 1 times 10 to, sorry, let's write that. 1 times 10 to the negative 9th molar. I don't like that 9. Okay, there we go. All right, last one. We're given the concentration of OH. Based on this, we can calculate our pOH by doing a negative log of 5 times 10 to the negative 7, which gives you 6.3 pOH. 3. And taking our pOH, you subtract that from 14, which gives you 7.7 pH. Take our pH, plug it into our equation to find the H plus, which is right here. 10 to the negative 7.7 is going to be 2 times 10 to the negative 8th molars. Based on this info, we can calculate our acidity or alkalinity, or how basic a solution is. pH of 5.8 is less than 7. It's going to be an acid. Excuse me. pH of 11.05 is going to be greater than 7, making it a base. pH of 5 is less than 7. It is an acid. pH of 7.7 is greater than 7 by 0.7, so it is a base. All right, let's move on to number 2. Excuse me. Number 2 says identify the acid, the base, the conjugate acid, and conjugate base. We're going to shorten this into A for acid, B for base, Ca for conjugate acid, and Cb for conjugate base. So we have to remember that for these, a definition of an acid is a compound that gives away a hydrogen or 2 hydrogens or 3 hydrogens, which we'll talk about in a little bit. Let's take a look at A. So A has NH3 plus H2O is going to produce NH4 and OH. So based on this information, we can go ahead and take a look at all of our compounds. So NH3 becomes NH4. So NH3 becomes NH4. Based on this information, we know that NH3 accepts a hydrogen, therefore making it a base. And since NH4 is a base on the left-hand side, the reactant side of the arrow, NH4 on the right-hand side of the arrow, on the product side, is going to be a conjugate acid, meaning that when you reverse this reaction, claiming that it goes to the leftwards direction, the NH4 acts as an acid that gives away its hydrogen to the water, making it NH3. So basically, when you determine that something is a base, it just flips into the conjugate of the other acid. So if you have a base, it becomes a conjugate acid. And since we know that H2O is now an acid, since it gives away a hydrogen to become OH, we know that this OH is going to be a conjugate base. All we do is basically flip. Take a look at B. We have HC2H3O2 plus NH3 is producing NH4 and C2H3O2. We know based on this that this H is being donated to the NH4, making this thing an acid. This thing that I refer to is actually acetic acid. Um, there's various ways to write this, so just recognize that this is acetic acid, and this is going to be acid, therefore making its corresponding compound on the right-hand side of the arrow a conjugate base. Now we know NH3 is a base since it accepts this hydrogen. We have 3 here, we have 4 here after the arrow, so this is going to be the conjugate acid. Third one, H2SO4 and 2H2O produces SO4 and 2H3O. So just real quick, we know H3O just basically means it's a proton. This is called hydronium. Hydronium. It's another way of just writing H plus. All right. So with this information, you don't really need it, but it's good to know just because. And since we know that H2, the one of the H's, or sorry, 2 of the H's from the SO4 is being donated to the proton, the H3O, the hydronium, and this H2SO4 now becomes just regular SO4. You know that is going to be our acid. Making the corresponding compound SO4 on the right hand side, the conjugate base. Now, H2O acts as a base. Therefore, its corresponding compound on the right hand side of the arrow is going to be the conjugate acid. Water is actually very special because water can act as both an acid and a base. If we take a look at our third example here, water acts as a base, and if we take a look at the first reaction here, we know that it acts as an acid. So because water acts as both an acid and a base, we know that the water is called amphoteric. Spell that correctly. Amphoteric, means that the substance or compound slash substance acts as both a base and acid. Acts as both acid and base. So this is a good terminology, a word to know, because water is special. It's one of the major examples of an amphoteric substance. So number 3 asks you, how would you determine the conjugate acid-base pairs in each of these reactions? So in order to determine the conjugate acid-base pairs, we discussed this a little bit. um, so if some compound, let's write this. So if some compound gives away a hydrogen, then that is an acid. If compound accepts H plus, it's a base. Now, if a compound is an acid, then on the opposite side, it's going to be, or sorry, let's just write this like that. So if it's an acid, it's going to be the corresponding compound on right side, on right of arrow, on product side, is going to be conjugate base. And same thing for this. The corresponding compound, this just means the thing above, corresponding compound on product side is going to be the conjugate acid. So all we do is just flip. So if you have an acid, it becomes a conjugate base. If there's a base, it becomes a conjugate acid. Moving on to question 4. What is the concentration of HBr if 50 milliliters was titrated with 79.44 milliliters of 0.275 molar sodium hydroxide, NaOH? So with this, we start with hydrobromic acid, HBr. So we know that the equation. This is also an equation not given to you on the test. So Ma, the molarity of acid, volume of acid, Va, and the amount of hydrogen, the moles of hydrogen of the acid, is going to be equal to the same thing of the base. So MbVb, and Nb. So this is a good thing to memorize. So memorize, because not given on test. Not given on test. Alright, so we can go ahead and solve this. So if we know that 50 milliliters of the acid, that is going to be the volume of the acid, and it's asking for the concentration of the acid, so that is going to be the Ma. And we have, we look at our HBr and look at the subscript right there of the H. So there is no 2, there is no 3, it's just an invisible 1. So we know that the N1, Na, is going to be 1. So with the base now, the NaOH, sodium hydroxide, we know that the volume is going to be 79.44, and the molarity is going to be 0.275. So with this and we know that there is no subscript after NaOH. It's not a 2, it's not a 3, it's just an invisible 1. So we know based on this here that the Nb is going to be equal to 1. So we have everything in here except for the first one, Ma. So all we do is solve. So Ma is going to be unknown. Ma times Va, 50 milliliters, times Na, which we know is 1, equals Mb, which is 0.275, Bb, 79.44, and Nb, which is 1. Solving this, we get 50 on this side. And we're just going to see Ma as X. This is just termed X. So 50X on the right hand or left hand side, and 0.275 times 79.44 is going to be 21.846. 21.846. So we divide 50 on both sides, and X equals Ma equals the concentration of HBr equals, there's a lot of equals, 0.437 molars. This is molars because it is the concentration. That is going to be our final answer. The concentration of the hydrobromic acid, HBr, is 0.437 molars. With this information, we can just go ahead and figure out number 5 as well. It says, find the concentration of NaOH. So we're looking for the M for B this time, since it's sodium hydroxide base. If 40.35 milliliters of 0.56 molar hydrochloric acid, so this is the Va, this is the Ma, and the HCl has no subscript after the H. There's no 2, there's no 3, there's just an invisible 1. We know that Na equals 1. Same for sodium hydroxide. We talked about this in the previous problem. The Nb is going to be 1. So I'm just going to side note, Nb equals 1. We have all our variables now. Oh, I was required to bring 90 milliliters, so that we are given the volume of the base. And now we have all the variables to solve our equation. So Ma Va Na equals Mb Vb Nb. So we take Ma, which we know is 0.56, 0.56, and Va, which is 40.35, 40.35, and we take the Na, which we determined here, that was 1, so we take 1 equals, we're going to solve for the concentration of NaOH, Mb, which is unknown, times volume of the base, 90 milliliters, we found that here, 90 times our N value for B, which is going to be 1 as well. We're looking at MB as X this time, so we're just going to term that X, and then we have 90X equals, and then if you do 0.56 times 40.35, you're going to get 22.596. So divide 90 on both sides to cancel, and now we have do this, and now we have X equals X equals 0.251 molars, and that is molars because X equals the MB, which equals the concentration of NaOH that was used. So that is going to be our final answer, 0.251. All right, let's move on to question number 6. This is a medium large unit, so it is going to be a little longer than the other ones. What is the difference between a monoprotic acid, a diprotic, and a triprotic acid? So as you know already, mono means 1, di means 2, and tri means 3. The pro, I'm just looking at the word pro, means proton, H plus. So basically, the monoprotic means that the acid is going to be giving away, or holding, that it's able to give away 1 hydrogen, mono, 2 hydrogens, di, and 3 hydrogens, tri. So the differences between a monoprotic acid, diprotic acid, and a triprotic acid is the amount of hydrogens it holds or can give away. of hydrogen, it can it holds slash can give away. All right, so hydrogen is going to be H plus. So let's give examples. So monoprotic acid, a good example would be hydrochloric acid, HCl. Diprotic acid, a good examples, H2SO4. And triprotic, good example is H3PO4. All right. What are the terms concentrated, dilute, concentrated slash dilute, and weak slash strong mean for acids and bases? So the term concentrated means that your molarity of the concentration, the concentrated acid, so the acid concentrated, is going to be greater than 6. Dilute means that the concentration of the acid will be less than 6. So we can just write on the bottom here, concentrated, which means it's a very high molarity. Molarity, which is M, capital M. Dilute means you just basically have a low molarity. Low molarity. And the borderline cut for this is going to be 6. If it's greater than 6, it's a high concentration. Less than 6, it's a low concentration. All right, let's break that a little. And weak acids means that it does not dissociate completely. Does not dissociate completely. So weak acids, like acetic acid, like vinegar, will not dissociate completely into its ions, but strong acids, like sulfuric acid or hydrochloric acid, will does dissociate completely into its ions. All right. Define and give an example of an Arrhenius acid and base. This is question 8. So we know that Arrhenius acids, there are 3 types of acids: Arrhenius acids, Bronsted-Lowry acids, and Lewis acids. So Arrhenius acids, Arrhenius acid AA, is going to be producing an H plus and giving it away. An Arrhenius base is going to be producing an OH. So the definition of Arrhenius acid and base is that it has to produce an H or produce an OH for an acid and base respectively. It's very simple. And just for fun, let us go over Bronsted-Lowry as well. Bronsted-Lowry acids, BLA, is going to be accepting an H plus, and Bronsted-Lowry base is going to be, Bronsted-Lowry acid is going to be giving away, an H plus, a proton, and Bronsted-Lowry base. This is the one that accepts H plus. All right. Number 9. Excuse me. How could foods or drinks be determined to be acidic or basic without using a specific lab test? Well, if you think about the characteristics of an acid or base, this is easily doable. An acid tastes sour. So, like, think of vinegar tastes sour, and bases tastes, it's going to be bitter. So think of like soap. Soap is very bitter. So, although in a lab setting, this is highly not recommended. This is like terrible practices in a lab. For our purposes, if you're not wanting to use a specific lab test, you can taste the solution. Once again, not recommended, but an acid will taste sour and base will taste bitter. And what happens with a base? What happens when a base is added to an acid? So, 2 things is going to be produced. Water is produced, H2O, and a salt, which is a metal plus nonmetal. So basically an ionic compound. The salt is not like NaCl. It is not NaCl, like table salt. It's just another word for metal plus nonmetal is reduced. All right, 13. What is the pH of a 0.25 molar solution of a weak acid, so weak acid, HX, with a Ka, the acid constant, of 6.2 times 10 to the negative 6? So with this, we have to start by writing out an equation. So an equation is going to be looking like, there's a little less space than I like to see, so we're going to move it to the side a little. All right, so the HX is going to be the acid, the weak acid. You want to do double arrows to signify that this is a reversible reaction. The HX is going to dissociate into H plus and X minus. The reason why H is plus is because it's a proton and X is a minus because the whole thing is a neutral. So we know that if H is a plus, X must be a minus in order to have the whole charge of 0. So with this information, we can set up a Ka. So this is a lot like the K stuff we've done in the past. You set the products. So let's write this: product over reactants. That's a bad bracket. Products over reactants. All right, so this is going to be products is going to be H plus and X minus, and the reactant is going to be HX as a whole. Okay, so the pH, we're looking for the pH. And so we're given that the molarity of the weak acid HX is 0.25. So we know that this equals 0.25. So what we can do is we can replace this with 0.25, which I'm going to do here. We also know Ka, which is 6.2 times 10 to the negative 6. We can set this up again using the fact that this equals this. So Ka equals, let's write this actually, 6.2 times 10 to the negative 6, and we still know that Hx is going to be 0.25. So 6.2 times 10 to the negative 6 equals concentration of H plus and X minus over 0.25. And we know that, let's erase this part and write it in red so I can explain this. So the concentration of H plus and X minus is this part, go up a little like this, okay? It's going to be, each concentration is going to be an X, and the concentration of X minus is also going to be just termed X. So when we establish this, it's concentration of H plus times concentration of X minus, which we know that it's just X each, just X squared. So times this, which becomes X squared on top. So this is actually X squared on top. So this equals X squared over 0.25, and we can solve this algebraically now. So let's move this constant over to the right. 6.2 times 10 to the negative 6. So times 0.25, 6.2 times 10 to the negative 6 times 0.25, which will give you x squared equals 1.55 times 10 to the negative 6 times 10 to the negative 6. And we square root this, sorry, and we cancel this x squared, and we make it x equals 0.00124, and we establish that each x is going to be the concentration of H plus and the concentration of X minus. So we know that this equals the concentration of H+. With this information, we have to grab our equation that we know from um, the first part we did together. In order to find the pH, which we're looking for, we have to use the equation. We'll just put it below. pH equals negative log of the concentration of H plus, which we know we found was this. So the concentration of H plus is 0.00124. Negative log that, and you will get the pH of 2.9 as your final answer. Oh, and before we know that pH of 2.9 is less than 7, which makes it a acid. Bingo. So pH is 2.9, and we know that it is an acid. And that is your final answer. And you are done.